Hi everyone. In this lecture we're going to be starting on a new chapter in our textbook shown here, Nanotechnology Understanding Small Systems. We're going to be working on chapter 7, which discusses nanoscale heat transfer and contains the very lovely quote, "Tomorrow's computers will be miraculously fast, but only if they do not melt when they turn them on." Anyway, so to start off, I'd like to talk about heat transfer in bulk materials. So you need to understand the properties in the bulk before you can look at what's happening at the nanoscale. So we're going to review the mechanisms of heat transfer, and then in this lecture we'll focus on conduction. So remember, and this is covered in many introductory physics course sequences, the concept of heat. So heat is the transfer of energy across the boundary of a system. And of course that net energy transfer will only take place if you have a temperature difference between the system and the surroundings. Okay? So heat, we'll use that term to represent the amount of energy that's transferred due to a temperature difference. So there's 3 different mechanisms responsible for energy transfer due to heat. Those mechanisms are conduction, convection, and radiation. So conduction is the transfer of energy via heat for 2 objects that are in direct contact with one another. In other words, the 2 objects must be touching in order for conduction to occur. Convection is when heat is transferred via a medium. So for example, a lot of heating systems, heat pumps, used forced convection, or the transfer of air throughout the room to heat the room. Okay, so you have to have heat transfer via a medium like air or water for convection. Radiation is the transfer of heat via electromagnetic waves. Unlike conduction or convection, there's no physical contact or medium required for that. So radiation is responsible for the heat that reaches our planet from the sun. Okay, now heat is just energy. Okay, heat and work are mechanisms of energy transfer, and so the units of heat match the units of energy, right, which is the joule. So heat is energy transfer, and how this energy is transferred is accomplished by one of 4 nanoscale things. Okay, so those 4 things are atoms, electrons, photons, which are particles of light, and phonons. Okay, phonons, or little sound waves. Okay, phonons are sound waves. So in that sense, all heat is nanoscale heat, right? Because it needs nanoscale things in order to do the heat transfer. So like I said, in this lecture we're going to talk about conduction, okay, which requires physical contact between 2 objects for heat transfer to take place. So how is this visualized on the nanoscale, right? So for example, in this image on the right from your textbook, what's happening here is heat is being transferred in a gas, all right? So you can imagine this as having a hot side and a cold side. So you put something hot in contact with something cold, and then the hot air molecules, hot gas molecules start running around. Now they've got more kinetic energy than the cold ones, right? And what happens is these hot gas molecules will collide with gas molecules that are colder, and when this collision happens, there's an exchange of kinetic energy between the hot and cold gas molecules during the collision. Okay. Now, it's important to understand that we said that there were 4 ways you could do it. You could do it, 4 nanoscale things that could do it. Atoms, right? Molecules, electrons. So these things that are colliding via conduction could either be molecules or atoms or conduction electrons. Okay, so this is the collision mechanism responsible here when I'm talking about this collision. Okay? Less energetic particles are going to gain energy during collisions with more energetic particles. And so that means that the energy will move from the hot to the cold as you make more cold molecules hotter through the collisions. So that's how it would happen in a gas. It's kind of easy to visualize in a gas. So what would happen in a solid? Okay, so here we're going to use the model of a solid as little balls, the atoms connected by little springs, which is the bond. Okay, so we're going to model this as balls and springs. So if you use this model, then you can think of heat energy, right, as the vibration of those atoms on their little springs. So hotter things are going to vibrate at higher frequencies than colder things. Okay, so that's how it works. So let's say that you start off and you've got a hot corner here up in the top, and then that causes this atom at top left to vibrate at a higher energy than the atoms around it. So it starts wiggling. But now it's connected via these bonds, which are springs, right? Modeled as a little spring. It's connected to those neighboring atoms, okay? So when it starts vibrating, the spring that it's attached to makes the next one vibrate, right? And so you can see how as more and more of the neighboring atoms pick up this higher energy, right? And then they vibrate more, and then they wiggle the ones next to them, and so on and so forth. And so that is how the energy transfer is done in a solid material, okay? Now, these vibrational energy waves are called phonons, okay? A single vibrational energy wave is a phonon. Now, in an insulating solid, phonons, these vibrational energy waves, are the primary carriers of heat, okay, in an insulator. In a conductor, you have those free electrons, and they can zip around and collide with things, as we talked about on the previous slide, all right? So electrons here as the carrier of heat, if you envision this as a metal, right? If you envision a metal with a bunch of conduction electrons in them, then what that would mean is that at a higher temperature, your conduction electrons are going to move faster than at a lower temperature. Now, in a previous lecture on Fermi statistics, we discussed how even at absolute zero, your conduction electrons are moving pretty fast. But as you get hotter and hotter, your conduction electrons move faster and faster, okay? Now, through collisions, the conduction electrons can transfer that energy to atoms and other electrons in the lattice, okay? And electrons and conductors, remember, they move at close to the Fermi speed, which is on the order of 10 to the 6th, but then it can be faster as they get hotter. Now, it's much faster. This rate of energy transfer is much faster than phonons, right? So if you think of a phonon as a vibrational energy wave, that's sound, right? And the speed of sound in metals is going to be a lot less than 10 to the 6th meters per second. And so that makes metals, in general, good thermal conductors compared to insulators, which only have phonons as the rate of phonons to carry the heat. So in general, metals are good thermal conductors because they contain a large number of electrons that are free to move through the material at high speeds. And those conduction electrons can transport energy from one region to another. If you don't have conduction electrons, you're an insulator, right? And so poor thermal conductors include things like asbestos, paper, gases. So asbestos, paper, solid materials, right? They have to transfer energy via wiggling, which wiggles the next one, which wiggles the next one. That's basically a sound wave, and so it can only move at the speed of sound in the material, which is a lot less than the Fermi velocity of, or the Fermi speed of conduction electrons. Okay? Now, we've been discussing conduction. In introductory physics, we show this equation for the rate of energy transfer via conduction. So that's the power, that's a curly P here for power, is equal to the amount of heat energy transferred Q divided by the time, delta T. Okay, so power is equal to Q over delta T. Q is heat, delta T is time, and then that is equal to Ka times d big T dx. Okay, so here K is the thermal conductivity of the material, so it's a material property. A is the cross-sectional area, and dt dx is how the temperature changes through the thickness, okay? So if you look here at this image that I had at right, you see this slab, right? The slab has some thickness to it, delta x, and then it has a hot side and a cold side, right? So energy will be transferred from the hot side to the cold side at the rate given by this equation. Now, it makes sense that if you have a thicker slab, that the rate will be slower, right? Thicker slabs mean slower rate of energy transfer. And it also makes sense that if you have a larger cross-sectional area, right, that the rate of energy transfer will be higher, okay? So then also you have this mediator of the thermal conductivity. So things with a higher thermal conductivity will transfer heat energy faster, right? And if the temperature difference is greater, then you'll also see a higher rate of energy transfer. So that explains this equation for the power or the rate of heat energy transferred between two sides. Okay, now this dt dx, d big T dx, that's called the temperature gradient, or the, gradient means change, right? So this is the temperature change from one side to another. And for a rod, you can just use the temperature gradient as a linear bit. So you can approximate a linear change in the temperature over the length of the rod. So we're going to use that approximation to work a problem here in a second. And so then your dt dx might go to delta t over delta x, where you just take the hot minus the cold temperature and then divide it by the width or the length of whatever object you've got there. So let's use that to work a problem here from your textbook. So we've got a copper wire, and it's 3 micrometers in diameter, and it's 300 micrometers long. At one side, there's a temperature of 35 degrees Celsius, and the other side, the temperature is 32 degrees Celsius. So we're going to calculate the rate of heat flow through the wire in watts. Now for copper, we're going to use the thermal conductivity of 400 watts per meter per Kelvin. Okay, so here's our equation. The power is equal to Ka delta T over delta X. We're going to use that linear approximation. K here is 400 watts. Oops, I got that up top, sorry. There we go. Watts per Kelvin meter, right? And then area would be the cross-sectional area. Now it's a wire that is 3 micrometers in diameter. So the cross-sectional area would be the area of a circle. So that's pi r squared. Now the diameter is 3 micrometers, and so that means that the radius is 1.5 micrometers. So here we have pi times 1.5 times 10 to the minus 6 meters squared is the cross-sectional area. Now delta T over delta X is the change in temperature over the length of the wire. It's 35 C on one side and 32 C on the other side. So that would be a change of 3 degrees Celsius from one side to another. Now Celsius and Kelvin have the same degree sizes, right? When you switch, you have a constant offset, right, of 273 Kelvin between one unit system and the other, but the degree markings are the same size. So 3 Celsius is 3 Kelvin in terms of a temperature difference. So that's our delta T, and then our delta X is the length of the wire, which is 300 micrometers, or 300 times 10 to the minus 6 meters. So putting all that into our calculators, you can get a power of 28 microwatts, right? And that would be the rate of heat energy transfer. So what are these thermal conductivities? You can read them off tables, okay? And so here's a table I took from an introductory physics textbook. You can see your thermal conductivity in watts per meter Kelvin or watts per meter degree C, because yet again it's a delta T, right? Aluminum is 238, copper 397, we used 400, close enough. Gold 314, iron 79.5, and so you can see that these metals have thermal conductivities on the order of 10 to the 2, right? Now, if you look, these are some non-metals with their thermal conductivities, and you can see that these thermal conductivities are many orders of magnitude smaller, right? So the thermal conductivities are a lot smaller because they're insulators, and so they only have phonons, right, and not conduction electrons as their mechanism of energy transfer, okay? And then here we have the gases, which also have low thermal conductivities. Now, you can calculate thermal conductivities, okay? So sometimes a material might have more than one carrier of heat. So for example, in a metal, you can have the conduction electrons transferring heat energy, but you can also have phonons, for example, in thermal conductivities, okay? So the thermal conductivity of a particular heat carrier can be calculated as follows. The thermal conductivity of a particular carrier is equal to rho CV lambda over 3. Okay, so what are all these things? Well, rho is the density of the carrier, C is the specific heat of the carrier, V is the average velocity of the carrier, and lambda is the mean free path of the carrier. And then sometimes you can use the volumetric specific heat, big C, which is rho times little c. So that would just be big C being lambda over 3. Okay? Now in our nanowires lecture, we discussed how to find the mean free path of a conduction electron. But what about gases, right? So the mean free path lambda is the average distance traveled before a particle has a collision. So if you assume that a particle has A as the cross section for the collision with another particle, then you can say that D here is the offset, right? So D is the diameter, and then the effective collision area would be A is equal to pi d squared. And this assumes that they have just a glancing collision with one another, where the edge of one catches the edge of the other, right? So that's the effective collision area. That's the maximum. Maximum, in other words, could be smaller than that. Now, as the particle moves, a certain volume would be swept out, right? So if you think of this, it would have the area of pi d squared, right? And as it moves along at some average speed v, right, it would move for some time t, right? And then that would mean that you'd sweep out basically a cylinder that has length v times t. Now the volume of that cylinder would be the area of the base times the length, which would be pi d squared times v times t, all right? So if we assume that a particle is contained in that volume V and it has collisions with n other particles in this windy zigzaggy path, then the length of the path would be capital L, right, which would be equal to the average velocity times the time, which would be equal to n times lambda, the mean free path, right? So n collisions times the average distance between collisions, which is the mean free path, n lambda, would be equal to the length, which would be equal to the average velocity times the time. Okay, so the volume of the path would be V is equal to L times A, where A is that area, that pi d squared, right? So we can use this equation here. LA would be equal to, as we saw earlier, N lambda times A, which is equal to VTA, right? Which would be equal to VT pi d squared, right? Because A is pi d squared. So if we rearrange now those two equations, we have N over V is equal to 1 over lambda pi d squared. Now, using our ideal gas law, remember we're doing all this for gases, so the ideal gas law from introductory physics says that PV is equal to nKT, where K in this case, K sub B, is Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin, one of our fundamental constants. So if you rearrange that, then N over V is equal to P over KBT, right? So now we have these two expressions for N over V, and we can equate them. N over V is equal to 1 over lambda pi d squared, which is equal to P over KBT. Now that would give us a solution for our mean free path lambda. Lambda would be equal to KBT over P pi d squared, all right? So that would give us an expression for our mean free path, but there is a problem. We used the average molecular velocity, but we didn't consider the fact that not only our molecule, but also the target molecules are moving, right? And the collision depends upon both of those things, the moving and the other target moving together. So if you want to correct that, you can use this relative velocity equation. Since the particles don't have to be approaching one another head on, right? If they were approaching one another head on, the relative velocity would be 2v, right? But since they don't have to do that, they can be moving at angles with respect to one another, the average relative velocity would be the square root of 2 times v, okay? And that changes the expression for the mean free path to match the equation in your textbook. So that shows you that your mean free path lambda is equal to KBT, Boltzmann's constant time to temperature, divided by the pressure, big P, square root of 2 times pi d squared, where d here is the diameter of our molecule. So that's our expression for the mean free path. So let's do an in-class problem to wind up this lecture and get cemented in our heads this idea of the mean free path of gases. Reading it together, very thin films are usually deposited under vacuum conditions to prevent contamination and ensure that atoms can fly directly from the source to the depositing surface without being scattered along the way. To get an idea of how few and far between the air molecules are in a thin film deposition chamber, determine the mean free path of a generic air molecule with an effective diameter of 0.25 nanometers at a pressure of 1.5 times 10 to the minus 6 Pascal and a temperature of 300 Kelvin. If the chamber is spherical with a diameter of 10 centimeters, how many times will a given molecule collide with the chamber before colliding with another air molecule? And how many air molecules are in the chamber? Okay, so let's do this. Part A first. Let's find the mean free path of this generic air molecule in the chamber. So our equation was lambda is equal to kBt over the square root of 2 p pi d squared. Okay? So as we stated before, K sub B is Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. T is the temperature, which was given in the problem as room temperature, about 300 Kelvin. Square root of 2 is in there. The pressure was given as 1.5 times 10 to the minus 6 pascals. And then, of course, we have pi times the diameter of the molecule d squared. So the diameter of our molecule was 0.25 nanometers. So that's 0.25 times 10 to the minus 9 meters squared. Plugging all that into our calculator, we end up with a mean free path of 9,940 meters, which seems ridiculously large. So that would mean that an air molecule would collide with the chamber 9,940 meters divided by the diameter of the chamber, or 99,400 times before it collided with another molecule. So this is one of the reasons why we like ultra-high vacuum, right? We like high vacuum and ultra-high vacuum because it keeps things clean, okay? Now, the next part says, how many molecules are there in the chamber anyway, right? So for that, we can use the ideal gas equation. PV is equal to N kBt. Rearranging that equation, we get N over V, the number of molecules per unit volume, is equal to the pressure divided by Boltzmann's constant times the temperature. So N over V, V here would be the volume of the chamber if we wanted to know how many molecules are in the chamber. So we have N over, now it has a diameter of 10 centimeters, so you can envision it as a sphere with a radius of 5 centimeters. So the volume for a sphere is 4/3 pi r cubed. So we have N over 4/3 pi times 0.05 meters cubed. That's N over V. Now we have that equal to the pressure over Boltzmann's constant times the temperature. The pressure is 1.5 times 10 to the minus 6 Pascal. K is 1.38 times 10 to the minus 23 joules per Kelvin, and T is 300 Kelvin, the temperature. So plugging all that into our calculator and solving for N, we can see that there's 1.9 times 10 to the 11th molecules in the chamber, which really isn't very much, okay? The pressure is pretty low. All right. Okay, well, I hope that was clear and you understood it. And if you have any questions, let me know, and I'll see you in class.